All right, we're starting something brand new. This is part of the theoretical definition for linearly independent and dependent. From here, we're going to discuss what's going on. Let C sub 1, C sub 2, C sub 3, C sub n belong to the set of real numbers, v scalars. And let set S equal the set of vectors v sub 1, v sub 2, v sub 3, v sub n, which belongs to the vector space. Then C sub 1 times vector v sub 1 plus C sub 2 times vector v sub 2, plus C sub n times vector v sub n equal the 0 vector. Using this, we can describe linearly independent. Now, linearly independent, I'm going to start writing as Li because this is too long to write. Just an FYI. If the only solution to C sub 1 times vector v sub 1 plus C sub 2 times vector v sub 2 plus plus C sub n times vector v sub n equals the 0 vector is when C sub 1 equals C sub 2, which equals which equals C sub n equals 0, then we know we have a linearly independent system. Now understand, we are talking about 0 because we're talking about the C's, which are scalars, not the 0 vector. If the only solution to this system right here, this is a linear combination basically, and the only solution we get is 0, then the set is linearly independent. So one more time. If the only solution you have to this linear... So one more time, I really want to stress this. If the only solution to this linear combination setup, which equals a 0 vector, and all of the C's equal 0. This is the only answer that you will ever get. The only thing, you can't get anything else, then set S is linearly independent. Learning about these, we will find out that the vectors are not scalar multiples of each other. The vectors will be all distinct. After this definition, and going through a few problems, we will find that vectors will not be scalar multiples of each other. The vectors will be all distinct, and that's how we know they're linearly independent. Now this will be great for a 2x2 because we can visually inspect it and determine whether the vectors are scalar multiples of each other or not. But if we have a 3x3 or higher, we're actually going to have to do some work. You're not going to be able to tell right away. One more time, according to the definition, the 0 vector is the only linear combination in which all of our constants, our C's, will equal 0. The vectors will form what is called a standard basis, or a normal basis, or just a basis. Those all mean the same thing. We will do this definition a little bit later. When we are dealing with square matrices in this chapter and beyond, if the determinant does not equal 0, this means that the vectors are linearly independent. In other words, these vectors are not scalar multiples of each other. And lastly, there will be no free variables. All right, once again, I want to bring up this starting of the definition for linearly. In this case, we're going to do linearly dependent. So this applies to linearly independent, and this applies to linearly dependent. It's all dependent upon the C's. So let's talk about linearly dependent. I'm just going to start writing it LD. It's just a lot faster that way, and I'm too lazy to write linearly dependent. You have a linearly dependent system when the vectors are multiples of each other. At least one vector is a linear combination of another in set S, and set S contains all the vectors. Going back to our definition, if it is possible that when you write this linear combination equals the 0 vector has a solution, at least one solution where one scalar, one of these C's, is not 0, then the set S is linearly dependent. If you have a square matrix and you find the determinant and it equals 0, then you know it is a linearly dependent system. Again, this only works with square matrices only. Also, with a linearly dependent system, there will be free variables, whether it's one or more. Let's look at linearly independent and dependent in R2 visually. Let's look at linear dependent first. Notice that these two vectors are scalar multiples of the other. In this case, this one is the negative of the other one, or vice versa. In this one, you notice that they are scalar multiples of the other, but in the same direction. They are making a line in R2. They are not making a parallelogram in R2, which would give us area, which gives us a determinant. There is no way to form a parallelogram like this. We're only forming a line, which explains why the determinant in R2 would be 0. So when you graph something like this and you get a line, this is a linear dependent system in R2. If we look at a linearly independent system in R2, notice that they are not scalar multiples of each other. They do not form the same line. Also, if we were to use the addition rule of vectors, we would actually see that we could form a parallelogram. A parallelogram forms area. You can find the area using the determinant. The determinant will not equal 0. Let's look at linearly dependent in R3. Notice that all of these vectors lie on the same plane. It does not matter if it's on the xy, the zy, or the xz plane. If they all lie on the same plane, this is called linearly dependent. It is not utilizing the z-axis. Notice that z here is 0. And so in essence, this is all you would form, x, y, 0. This only forms a plane in R3. In a way, you could actually state that it does not form volume. We are not utilizing all of R3. If we utilized R3, we would actually have some vector or two off of this plane to help us form volume to be in R3. Our z value would not be 0. Now let's look at this example, linearly independent in R3. Notice that two vectors lay on the same plane, but one is off it. Because of that, this value here, where this vector points at, let's just call this a point out somewhere in R3. This has a z value. Because this has a z value, we're now in R3. We can see that we could form some type of volume. This would, if we were to form and put these all together, we would form a cube. That would utilize R3 space, which means, again, we could find the volume. If we can find the volume in R3, it is a linearly independent set of vectors. We're going to do a few examples to explain linearly independent and linearly dependent not graphing. We are given the set S, which contains these vectors right here. And we want to know, are these vectors in set S in R3 linearly independent or linearly dependent? Since it will form a square n by n matrix, we can find the determinant, and I will let you know it's 0. But let's use Gauss-Jordan row-reduced echelon form to get some values and use the idea of linear combinations to help us understand the concept of linearly independent and linearly dependent. Linear combinations can help us understand linearly independent and dependent, but understand they are separate concepts. So linear combinations will make sense of this whole idea, but linear combinations and linearly independent and dependent are separate concepts. That's all I'm trying to say. So the first thing that I'm going to do is I'm going to put my vectors in a matrix. And a lot of students ask me, how do I do that? Whenever you have vectors, you do column vectors in a matrix. Now, I'm setting it equal to 0 because we're doing row-reduced echelon form. Making it a homogeneous system is okay. We don't change anything. I'm using the augmented matrix to help us solve and do linear combinations. Overall, though, if you wanted to find the determinant, as you guys know, just use the coefficient matrix to find that. Reducing this matrix, I get this. And notice that I got a whole row of zeros. Now, if it was a coefficient matrix, this is what I would get. So understanding one of the properties of determinants is if I have a whole row of zeros or a whole column of zeros, the determinant is 0. Now that I've row reduced my matrix, I'm going to use parametric form so that we can start the whole idea of linear combinations. So linear combination outlook. What are the values of C? This is C sub 1 times vector V sub 1 plus C sub 2 times vector V sub 2 plus C sub 3 times vector V sub 3. And it equals the 0 vector. Using our final matrix, what we're going to do is we're going to use parametric form. So C sub 1 minus 2C sub 3 equals 0, hence the reason why I put the 0 vector here. That means when we solve for C sub 1, we get 2C sub 3. C sub 2 minus 3C sub 3, right here, equals 0. C sub 2 equals 3C sub 3. We now have our setup getting ready for parametric form. Here, C sub 3 is our free variable, and we're going to let C sub 3 equal t, which belongs to the set of real numbers. Free variable, again, is anything on the right-hand side. Hence, C sub 3 is now going to equal t. We're now going to get a parametric representation. So now we can write a parametric representation so each of our C sub n's, in other words C1, C2, C3, can be written in terms of t, and we will get the following. Again, here is what we had. We had C1 is 2C sub 3, C2 is 3C sub 3, and C sub 3 we're going to let equal t since that is our free variable. Replacing C sub 3 with t, we get C1 is 2t, C2 is 3t, and of course C3 is t. We have a parametric representation of our constants. So our set notation using the parameter t would be the set, and you have a point here, 2t, 3t, and t, such that t belongs to the set of real numbers. This is your set notation. As far as linear combinations are concerned, yeah, it's a linear combination. But we're going to look at the linear combination definition for our problem to help us understand linearly independent and linearly dependent a bit better. Here is our linear combination definition for our example. C1 vector V1 plus C2 vector V2 plus C3 vector V3 equals vector W. Simply the linear combination definition. I wrote C1, C2, C3, V1, V2, V3 because I have 3 vectors and each of these vectors needs a coefficient of C. What I'm going to do is replace each C, in other words C1, C2, C3, you can also call this C sub n, with its parametric form or parametric representation. So I'm going to replace C1, C2, and C3. Now I have 2t times vector 1 plus 3t times vector 2 plus t times vector 3 equals vector w. Here's an interesting thing to know about this problem. I can put any number in for t, which means if I put any number in for t, which is an infinite amount of numbers, I will get an infinite amount of vector w's. So, notice that we can now write this answer in infinitely many ways. So this problem, set S, that we were originally given with these vectors, is considered linearly dependent. We have one less vector than we started out with. The vector that dropped out was a multiple of the other row or rows. We have a free variable by looking at it as a linear combination. That is very important. So by having a free variable, I have proved to you that this is linearly dependent. Here's a question that I often get from students. Why can't it be linearly independent? I could let t equal 0 and I get zeros for each constant c. Wouldn't that make it linearly independent? Good question. Let me give you my answer. This is why I brought in the idea of linear combinations. You can let t equal 0, where t belongs to a set of real numbers, and yes, you will form a 0 vector. However, it's not the only vector you can form. We can let t equal -2, t equal 5, t equal 1/4, etc. We can form an infinite amount of vectors because we have the parameter t. If we can form more than one vector besides the zero vector, then the problem is linearly dependent. So again, it's not about forming just the zero vector. Can you form more than that? If you can, it is linearly dependent. I know I'm repeating myself, but you have to understand this is a hard concept. If you can form another vector w from our linear combination, then the problem is linearly dependent. If the only thing you can form is the zero vector, then the problem will be linearly independent. A problem cannot be both. New example. Is the set S linearly independent or linearly dependent? Here set S, they gave us two vectors in R3 space. Why are they vectors? Because set S represents the set of vectors by definition. By looking at these two vectors, they will not form a square matrix, so we cannot use a determinant. So let's use Gauss-Jordan row-reduced echelon form to help us understand the concept of linearly independent and linearly dependent when we're given an n by m matrix, a rectangular matrix, not a square matrix. So once again, I was given a set of vectors, so I'm going to set it up as vector 1, vector 2, and because I'm doing Gauss-Jordan, I'm going to set it equal to the zero vector. It's a homogeneous system. Setting it equal to 0, again, does not change anything. Row reducing it, I end up getting this matrix right here. And notice that I put in our constants C sub 1 and our C sub 2. Again, I'm getting ready for linear combinations. This set is linearly independent. And the question that I get is why? Let me tell you. We are given two vectors. These two vectors help us form C sub 1 times vector V sub 1 plus C sub 2 times vector V sub 2 equals vector W. That's the linear combination definition. Where if I solve for C sub 1 in our matrix right here, we see C sub 1 equals 0, and we see C sub 2 equals 0. If we plug in our values for C sub 1 and C sub 2 into this linear combination, here is C sub 1, which is 0, times vector V sub 1, plus C sub 2, which is 0, times vector V sub 2. What does that equal? We get the 0 vector. By definition, the set of vectors that we have are linearly independent. The only thing that I got was a 0 for C sub 1 and a 0 for C sub 2. I did not get a free variable. The only thing I can form is 0 for C1 and C2, linearly independent. New example, is the set S linearly independent or linearly dependent? Set S, we are given the following vectors, 2, 1, negative 3, 2, and 1, 1. As we can tell, this will not form a square n by n matrix, so finding the determinant is out of the question. We're going to have to use Gauss-Jordan row-reduced echelon form. Setting up my matrix again, every time you're given vectors, vectors are column vectors. 2, 1, negative 3, 2, 1, 1, set it equal to 0. And solving it, I end up getting this matrix right here. You got column 1, column 2, column 3. You have C sub 1 times vector V sub 1, C sub 2 times vector V sub 2, C sub 3 times vector V sub 3. This forms a linearly dependent system. We were given 3 vectors. 2 of our vectors form the basis, but the third did not. Now this is an extra note. Again, you do not understand a basis yet, but do me a favor, when you go to the video, come back to this one and it'll make sense. Or go back to your notes, whichever one you want. But this is an extra note that we're going to learn about in another video here shortly. Here is what we really want to know. The third vector, or the third column, will form our free variable. Ah, we have a free variable. Aha. I have a little bit of extra work for anybody who's doubting what we're getting. From our matrix, we ended up getting C1 plus 5 over 7, C sub 3 equals 0. Solving for C sub 1, we get negative 5 over 7, C sub 3. And I can do the same thing for C sub 2. Notice C sub 3 is on the right. That is my free variable. Yeah, I got a free variable. What I'm going to do then is I'm going to let c sub 3 equal t, and of course t belongs to the set of real numbers. Now we can write a parametric representation where each c sub n, in other words c1, c2, etc., is in terms of t. Here's what we got from the matrix, c1, c2, and c3. And as you know, we're going to let c sub 3 equal t, which belongs to the set of real numbers. Replacing c1 and c2 with t, we end up getting c sub 1 is equal to negative 5 over 7t, c sub 2 is negative 1 over 7t, and c sub 3 is t. Our set notation using the parameter t would then be, we have the set and we have the point, negative 5 over 7t, negative 1 over 7t, and t, such that t belongs to the set of real numbers. So this is our set notation. Because t can represent any number besides 0, we know that set S is the set of vectors, is a linearly dependent set. As far as linear combinations are concerned, yes, it's a linear combination. Here's our linear combination definition for our example. Here is our definition for a linear combination. I'm going to replace C, in other words C1, C2, and C3, with its parametric representation. So all I did is I replaced C sub 1 with its parametric representation, C sub 2 with its parametric representation, and C sub 3, of course, with t. Choosing any number for t, we can write an infinite amount of combinations. This is why the set S is linearly dependent.